Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good morning to all of you. Alright, so first of all, I would like to thank to MACE, Malaysian Society for Automatic Control Engineers, for inviting me to give a talk or to share some part of my research. Okay, before that, let me introduce myself. My name is Mohd Shahrieel Mohd Aras. Currently, I'm the chair of IEEE OES Malaysia chapter and also head of mechatronic department, Faculty of Electrical Engineering, UC Technical, Malaysia, Melaka. For today, I would like to share some part of my research that we call the additive simplified single input fuzz logic controller design. Okay, so this is my presentation outline for today. So first, I would like to introduce my research group. Then I will explain on the single input fuzz logic controller. Then next, for the remotely operated vehicles to verify the effectiveness of the proposed control scheme. Next, I will explain on the some improvement that we do on the single input fuzzy controller. Then this single input fuzzy controller will be tuned using the particle swarm optimization. Next, we introduce one techniques that we call the additive simplified single input fuzzy controller, or we call the ASIFRC, conclusion and references. So this is my research group that we call the Underwater Technology Research Group, or we call UTRG. Okay, actually this Underwater Technology Research Group, UTRG, is one of the research group from Robotics and Industrial Automation, RIA, under the Center for Robotics and Industrial Automation, CERIA, in Faculty of Electrical Engineering, EUTMs. Okay, as you can see in the slide, so we have already developed a lot of underwater platform, okay, such as ROV, remotely operated vehicles, and also we have autonomous underwater vehicles, AUV. Also have the underwater gliders, okay, underwater crawler, and also we have the pool and river cleaning robot, and also we have the integrated ocean observation system. So this is some part of our underwater platform, okay, on our research group. Next, we go for the single input fuzzy controller. Okay, actually, this single input fuzzy controller is inspired from the conventional fuzzy logic controller based on the signal digital method and piecewise linear control surface. Okay, the signal digital method proposed by introduced by Choi in 2000, and then piecewise linear control surface method introduced by Ayub in 2009. So the conventional fuzzy controller for the 7x7 control metric rule is simplified into the single input with several rules that we call the single input fuzzy controller. Okay, before this we have 49 rules. Okay, 49 rules. Then we simplify into the 7 rules. Okay, so this is some advantages of the single input fuzzy controller. It's a simpler method. Okay, and then only one input variables. Then we call the seesaw system. Okay, that means we have only single input, single output system. And then rule table will be in one dimension space. Okay, and then the number of tuning is greatly decreased. Before this, I mentioned to you, so we have 49 rules because we use 7x7 control metric rules, reduced to the 7 rules. Okay, that means the number of tuning will be greatly decreased. And then the conventional complexity is the mitigated, and then it is equivalent to the steady mode control. Okay, so this is some advantages of the single input fuzzy controller. Right. So as you can see here, this is the conventional fuzzy controller. That means we have two inputs. Okay, for example, input number one we declare as the error. Okay, so this is input number two. We can declare as the change of error or data error. And then normally we use the Mamdani as a reference engine. And then this is the output. Okay, you can see the membership function here. So here will be on the input one error, and this is input two. We call it data error, and also the output. Okay, so as you can see, the table one is a 7x7 metric rule of the conventional fuzzy controller. Actually, this is a default rule. Okay, from this table you can see, okay, we have the diagonal line here. Okay, we have the diagonal line. You can see here is the diagonal line. All right, and then also we have another diagonal line here. Okay, another one. Okay, this part maybe we can declare as the saturation region, and also this part we call the saturation region. Okay, but you can see this is the main diagonal line we call the LZ, and then parallel with we have the parallel with and L and S and so on. Okay, as you can see here. Okay, this we call the signal distance method. Okay, proposed by Choi. Right, from this diagonal line here, so we introduce the straight line here, the equation of straight line, and then from straight line we have another parallel with diagonal line. So we have the distance between the diagonal line here. For example, this is diagonal line for LZ, and this is a diagonal line for LPS. And then this the method simplified the number of input to the single input variable known as the distance d here. Okay, so the distance represent the absolute distance, magnitude of the parallel diagonal line, okay, which is the input set for the input 1 error and data error lie from the main diagonal line. So this is the main diagonal line. We call the LZ. Right, so this is derivation. All right, derivation from the main diagonal line to get the t, to get the distance here, absolute distance. Right, so this derivation come from Choi in this paper, okay, design and stability analysis of single input fuzzy controller. All right, so you can see detail on this derivation from the main diagonal line here is the straight line, and then until you get the d here. Okay, all right, so from diagonal line, we calculate the distance as you can see. So this is the single input physiologic controller structure. All right. So the first of all, you can see is a you can declare as the input 1 error, and this is data error. Okay, and then this is the d. Okay, the distance. And then from okay, this one is we call the signal distance method, and this one is a piecewise piecewise linear control. Okay, piecewise control surface. Okay, and then we be convert into lookup table lah. Okay, this one the control surface can be approximated as a piecewise control surface can be constructed using the using a simple lookup table lah that proposed by Ayub in 2009. Okay, so and then this is the scaling factor lah, scaling factor. Okay, as you can see, when we convert into the block diagram in the MATLAB, so this is a single input fuzzy controller. So this is for input 1, input 2, and this is D, and this one we call the scaling factor lah. So maybe we can declare this one as a K1, declare as the K2. Okay, this is D, and also this one is we can declare as the K3. Okay, so this is a single input fuzzy controller parameter, and will be implemented in the MATLAB lah. Alright, so next I will explain on the ROV, the plan that we use to verify the effectiveness of the proposed control scheme. Okay, as you can see, we have on our research group we have the first ROV here, second ROV, third ROV. Alright, so for this simulation we use this first ROV because of stability lah, because second and third ROV is not stable. That's why we just focus on the first ROV. Okay, first, what is the ROV? Actually, ROV is the stand for remotely operated underwater vehicles. Okay, actually the ROV is unequipped, highly maneuverable, and operated by the ROV pilots on the underwater platform lah. Okay, normally ROV are linked to the platform by tether, sometimes referred to as the umbilical cable, the group of cable that carry the electrical power, okay, video or data signal to the ROV pilot lah. Okay, so normally ROV used for in deep water industry such as oil and gas exploration, telecommunication, okay, geotechnical investigation, mineral exploration, and so on. Okay, so actually the control system of the ROV is very interesting and challenging problem. So this is primarily due to the difficult and unpredictable environmental disturbance, okay, that existed on underwater. So designing a suitable controlling method of the ROV is challenged due to unpredictable nature of underwater dynamics and difficulty in measuring ROV parameter. So in this research, uh, the focus area was controlling an ROV in heave axis motion trajectory, or sometimes we call the depth motion or depth control, to maintain the ROV in the desired position. Okay, so the function of if axis motion is to maintain the ROV position at specific depth and ensuring its stability. Also, we call the station keeping or auto depth control. Okay, for vertical trajectory, or sometimes we call the depth control, the overshoot in the sister response will be one of the factors to be measured. Okay, because the overshoot is particularly dangerous to the ROV vertical territory and may cause damage to the both to the ROV and to the inspected structure. So this is a ROV model matrix. Can we see this one on the equation 1? All right. So underwater vehicle motion model can be derived from the factor that affect the dynamic equation of underwater vehicle in the fixed body frames. So the dynamic this can be derived can be derived from the Euler and Newtonian and Lagrange formulation. So you can see the dynamic of 6 degrees of freedom underwater vehicle can be described in following general form, as you can see in the equation 1. So this derivation you can see on the reference 4. Okay, so actually this is a standard for unmanned underwater vehicles. Okay, where is M is the 5 times 5 inertia metric, including the hydrodynamic added mass, and then we have C. C is the Coriolis and centripetal force. Okay, we have the hydrodynamic damping metric, and G is the vector of restoring force and moment. Okay, equals to B. B is the control matrix. Okay. Okay, since the ROV is considered to be fairly symmetrical and travel at low speed, okay, the decoupling for the vehicle degree of freedom is valid. Okay, so the decoupling means that the Coriolis and centripetal, okay, the C terms metric become negligible, or we can ignore, and then consequently we can eliminate from the dynamic model. So you can see, so we eliminate from this equation, from the equation we eliminate the C, the Coriolis and centripetal force. And then the simplified, okay, more dynamic model for the ROV become, okay, and then we focus on the Z-axis, on the motion on the Z-axis here. Okay, so as you can see in the figure C is the model of ROV in the MATLAB, okay, simulating, and then this is some parameter of our ROV. Okay, some parameter we can get from the analysis, okay, using the software, and some of the parameter we can get from the experimental data. Okay, all right, so that I mentioned to you, so some part of the from the single input physiology controller, we do some improvement from the standard single input physiology controller that proposed by reference 15. There is Kashif, based on this paper, single input physiology controller for unmanned underwater vehicles. Okay, from this paper, so they use the 7 rules. Okay, you can see this one, the table 3. Proposed by 15. They use the 7 rules. So in our part, we try to reduce. Okay, we try to reduce to 5 rules, only 5 rules. The first initial, they use the 7 rules. Then we try to do some improvement. Okay, we reduce to 5 rules. Okay, but the value here, okay, the value for D, we use the formula lah, as you can see before this, to get the D. Alright, so this is a response, system response based on reduce seesaw rules table into 5. Okay, this one to 5, and this one for using the 5 rules. Okay, this one is 5 rules. Alright, as you can see, if you use the 7 rules, there is no overshoot here. Okay, you can see no overshoot. Compare then, if you use the 7 rules, there is a very small overshoot happen here. But for the rush time, you can see the rush time, I think around 7 seconds. Okay, 7 or 5, around 7 seconds. Compare then, we use 7 rules, so the rush time around 15 or 17. Okay, around 17 seconds. That's why some improvement when we reduce the number of rules, but we introduce the overshoot here. So we try to do another improvement to eliminate this overshoot. Okay. So next we try to introduce another one that we call the reference model. Okay, this reference model act as the input filter. Okay, so the input signal can follow the set point as needed. So this is a reference model that we use in our system. Then you can see the result for the system response with reference model. So no overshoot happen here, and also uh, will be good on the system response around 14 seconds, around 40 seconds. Compare then we use 7 rules around 70 seconds. But for if you use 5 rules, 5 rules not without the reference model around 7 seconds. Okay, so next improvement that we do on the single input file controller, we introduce on the lookup table, we introduce that we call the linear equation. Okay, so actually this is lookup table. Okay, lookup table, and then we introduce linear line on the control surface in the lookup table. Okay, this one we can use the Excel. Right, so on this linear line we can get the equation. So the equation here is a 0.277x minus 1.1109, and then we convert into the plot diagram in the MATLAB Simulink. So this is a linear equation, and then we change to in our lookup table. Okay, so this is the result. You can see this is the result. Okay, the system result using the linear equation as the lookup table. So very good in the system response. You can see it's no overshoot here, and we have the good on the rest time, and also steady state error. Right, so actually the parameter that I mentioned to you, the parameter for single input file controller, we have before this we have K1, K2, K3. Actually this parameter is tuned by PSO lah. Okay, the particle swarm optimization algorithm is applied to tune the parameter of single input file controller for that control of the ROV. Okay, so we use the PSO to optimize, the parameter of the PSO. So for PSO we use two techniques, two methods and improvise of PSO, such as a priority based fitness PSO, and then another one is the binary priority based fitness PSO. Okay, so the priority on the PSO, we set the priority lah. The set priority. The first that means to we focus on the overshoot. Okay, because our objective is to reduce or to eliminate the overshoot in the system response. Then we focus on the sending time, and also is the steady state error. Okay, after we get the K1, K2, and K3, we do some analysis using the intersection and average value lah, based on the PSO value algorithms. Okay, so this is an improved PSO approach lah. So you can see the first priority that I mentioned to you, we focus on the overshoot. Then after that, go for the setting time and then steady state error. Okay, so this is a PSO plot diagram in the MATLAB. Okay, so initially you can see, so we optimize the parameter K1, K2, and this one is a D. The D come from the formula, and this is K3. Okay, initial we optimize the three parameter. After several run of the PSO, so we found that the K3 is almost constant, That, and then we declare as the K3 is the constant value lah. It's the constant value. Next, we just focus on the K1 and K2 using the PSO. Okay, so as you can see, the table 5 is the comparison between the intersection and average value lah, the analysis that we do, that we done based on the parameter that we get from the two technique on the PSO. Okay, you can see here the K1 using the PF PSO and this K1 for BPF PSO. So you can see both okay almost similar lah, almost similar. For example, like intersection K1 120.7, okay, parameter for K1, and for average 120. All right, so almost similar lah. Compare then K1 using the BF PSO, BPF PSO, so 38.21, for average is a 37.85. Okay, so this is for K1, K1 using the PFPSO, and this is K2, PFPSO, and this is K2 BPFPSO lah. And then we try to run again. All right, so this is the result lah. As you can see, figure 15 is the sister response using the average. Okay, this one for average. Okay, and then another one is intersection using the tuning result by PFPSO. Okay, this one for 15 the PFPSO, and figure 16 is the BPFPSO lah. All right, so from the both you can see the performance for sister response is I think the PFPSO is better compared than BPFPSO. Okay, in terms of overshoot, in terms of statistical error, and in terms of rush time, compared than we use the BPFPSO. Okay, also in our research we try to implement another controller such as NNPC, neural network predictive controller, and also we try to use the PI controller, and then single input fuzzy controller, also with LQR and improvement single input fuzzy controller. Okay, so as you can see, figure 17 is the comparison of the system response for the all control applied. Okay, so as table 6, you can see the computational time lah for every controller apply lah. As you can see here, so an improvement is very faster. Okay, around 10.45 seconds compared than we use the NNPC. NNPC very longer time, around 450 something second lah. Okay, and then you can see the performance. Okay, the performance for rush time, certain time, and overshoot here. So the end improvement is can eliminate the overshoot. Okay, can eliminate the overshoot. But as you can see on the rush time, okay, the NNPC is better than an improvement single input fuzzy controller. Okay, so for example, like NNPC is around 50 seconds, but NNPC around 50 seconds, and improve single input fuzzy controller is around 60 seconds. Okay, so that's why we try to introduce another technique to improve. Okay, to improve the rush time, and also to eliminate the overshoot. Okay, that we call the adaptive simplified single input fuzzy controller. Actually, this inspired word adaptive come from the concept of adaptive controller. And then the single input fuzzy controller adaptive simplified single input fuzzy controller technique work by combining different setting of the single input fuzzy controller that was optimized by PSO. Okay, the optimum parameter for every case is used to test the ROV on different set point. And then the adaptation of the different set point based on the previous optimum parameter tuned by an improved PSO algorithm. Okay, so that the new technique that we introduced, okay, to eliminate the overshoot and to improve the rush time lah, so that we call the additive simplified single input fuzzy controller, or we call the ASIFRC. All right, so you can see figure 15, figure 18 here. So this is the sister response for the set point 1 tuned by PSO. First we tune by PSO, so we put some step response here, okay, and then you can see for the sister response for set point 2 on the parameter set point 1. That means, okay, first K1 and K2 we use the PSO, and then after get the parameter K1 and K2 here, so we use for use this parameter for the set point 2. And then you can see for the figure 20, so we try to tune using the PSO. Okay, we try using the PSO, and then figure 21, set point 3, okay, another set point, okay, another set point you can see here. We use the K1 here, okay, K1, K2 from set point 1, okay, so from set point from K1 here and K2 here, okay. All right, so next figure 22, okay, and then set point 3, we use the set point 2, that means the parameter from set point 2, K1 and K2 from set point 2. And then figure 21, okay, sorry, this one 23, this one 24, okay, this one 25. Right, so figure 23, set point 3 is tuned parameter by PSO. So this one you use the PSO, and then you can see we try to use another set point, okay, another different set point here. So, but based on the set point, okay, set point 1. So this one K1 and K2 based on set point, set point 1. And then you can see this one we use same set, different set point here, but based on the set point 2, okay, based on K1 and K2 based on set point 2. All right, so and then figure 23, okay, the set point 3 we use the set point 2, but I mean K1 and K2 we use the from the set point 2, the parameter from set point 2. And then you can see here for set point 3, okay, so this one we try to use PSO, okay. And then figure 25, you can see is this one we use the K1 K2 from set point 1, K1 K2 from set point 1 parameter, and then this one K1 K2 based on set point 2, okay, based on set point 2. All right, so then you can see on the sister response, okay, this one we using the K1 K2 based on the set point 3 parameter based on set point 3. Okay, and then this one we try to tune using the PSO. All right, so as you can see in table 8 and table 9 is the result okay, the parameter obtained from the set point 3, okay, so you can see this one, and then also table 9 is the result for the different, okay, with different set point. All right, so for value for K1 and K2, and then after we get this, we do some analysis. You can see here, this is some analysis we do on our value of K. So we try to plot, okay, plot in our K1 and K2 here. So this is a K1, okay, this is K2. As you can see here, so this parameter is almost like linear, okay, almost like linear. That's why I use in the Excel, so to get the linear line here and also the linear line for the K1 and K2 lah. And then from this one, okay, we can conclude that the parameter K1 and K2 can be similar like lookup table or similar like piecewise continuous surface lah, okay, can be constructed using the lookup table. So okay, that our conclude for this technique lah. That means we can convert K1 here, K2 here into the lookup table. Okay, that is our conclude for this analysis. Okay, that means we can convert K1, K2 into the lookup table. This is maintain D and this is scaling factor. Okay, this figure we call the additive simplified single input fuzzy controller. Okay, that is the main objective for my research lah. So we try to how to get the value of K1, K2. Okay, so at the end we can get this K1, K2 into the lookup table, or we can represent as the linear equation. Okay, as you can see here. All right, so this is the result for proposed, okay, control scheme. that we call the additive simplified single input frequency controller. So you can see figure 31 and 32. So with different set point, you can see different set point, but you can see the both can no overshoot happen. Okay, no overshoot, and very good in the rush time and also steady state error. Okay, as you can see from the figure 31 and 32. So this is a system response for the depth control of ROV using our proposed control scheme lah. That is additive simplified single input frequency controller. Alright, so as you can see, this is a controller simulating lah, block diagram using the MATLAB. So this is our ROV model. Okay, and then but this part we try to introduce environmental disturbance. Okay. So this part we call the environmental disturbance. So this part we can you get from the references. Okay, so this is a single additive simplified single input controller simulating block diagram. Okay, so this is the result. Okay, the result for system response for additive simplified single input frequency controller, and we try to compare with tuned by PSO lah. So you can see a lot of improvement, a lot of improvement compared than we use the PSO lah, tuned by PSO. And then this is 35 is the system response for additive simplified single input frequency controller with disturbance. So you can see our ROV still can maintain at the certain depth lah. That's mean maintain at the 5 meter depth, for example. This is for simulation lah. Okay, almost if you see on the real time, so our ROV is look like maintained at the desired position. Okay, so that I mentioned to you. So this is the real time. Okay, this is real time ROV, but the limitation. So because of our lap tank test is around 1.8 meter depth, so that's why we just focus on 1 meter depth lah. Okay, that's why focus on 1 meter depth. Okay, you can see. So this is a system response for the depth control of ROV using the single input frequency controller at 1 meter. So this is we try to several testings per experiment. Okay, you can see here. So also we have some noise here. Okay, but actually if you see on the video, our ROV is like maintain at the 1 meter. Okay, but this one data is come from the sensor. So the sensor we can and then we plot to the MATLAB. Okay, so that the actually the data lah. So but on the real time, actually the ROV will be, you can see almost maintained at the 1 meter. Okay, and then another figure 36 is the comparison from simulation. Okay, and real time lah. Okay, you can see simulation is no overshoot compared than real time lah, but the both is almost close together lah, simulation and real time. Okay, and then we try to implement our controller to other model of ROV, such as first we try to implement in the macro ROV. Okay, so you can see this is a simulating for the macro ROV using the single input additive simplified single input frequency controller. Okay, on this part, this is our contribution, our controller scheme. Okay, and then another one we try to implement our proposed control scheme to 6 degree of freedom RRC ROV2. Okay, this one you can see. Okay, this is a simulation using the MATLAB. Okay, and also we try to on the Gaymarine Pluto-Gigas ROV. Okay, implement in our proposed control scheme. That is the additive simplified single input frequency controller. And last, we try to implement on the deep submerging rescue vehicle. Okay, you can see. So this is our control scheme, our proposed control scheme. Okay, and then we see the performance for every model. Okay, so this is a comparison system performance of that control using the single input frequency controller for every model. For example, like macro ROV, we have the non-linear RRC ROV 2, and then we have Gaymarine Pluto-Gigas ROV, and we have the deep submerging rescue vehicle. So as you can see here, so the main objective, we want to eliminate the overshoot. So our proposed control scheme, that is the additive simplified single input file controller, can eliminate all the overshoot. Okay, all the overshoot, no overshoot happen on the system response. Okay, but maybe some of the rest time and certain time is not so good compared than we implement in our model. Okay, but our objective here is to eliminate the overshoot, because we try to focus on the depth control. The priority of our research is more on overshoot. That's why we can eliminate the overshoot. Okay, so last is but not least is my conclusion. Right, so the investigation on the effect of the tuning the variable parameter for single input file controller to improve the performance of the system response for the depth control of ROV. So here we introduce the we reduce number of rules, okay, from 7 to 5 rules, and then we try to introduce the model reference, okay, to reduce the overshoot, okay, to eliminate the overshoot. And then another one, we try to change lookup table to the linear equation. Okay, that is some improvement on the single input file controller. And then an improved PSO algorithm based on the priority based fitness and binary priority based fitness approach was implemented to find optimal single input file controller parameter lah. So we use the PSO to find the optimal parameter for K1 and K2 lah. Okay, and then a new method that we call the additive simplified single input file controller, ASR for depth control of the ROV has been tested, and also in our ROV, okay, ROV1, and also we try to another ROV lah. We have another we try to 4 type of the ROV, different ROV. Okay, so this is my references. Right, so thank you very much for your attention. Okay, so if you have any question, okay, any question, or you want to discuss something about research, okay, you can email to me. All right, so thank you very much. Okay, Assalamualaikum warahmatullahi wabarakatuh.